We are now recording.
Cool.
All right. Hello, everybody. Welcome back. I hope you enjoyed your pizza. Again, if anyone is practicing Ramadan, we've set aside some pizzas for you later. Just let us know if you want to have them. Or if you're just hungry later, just let us know, I guess. Before we start the talk, we forgot to mention this a bit earlier in the day, but we've decided to award a little prize to the biggest WIMP. So whoever amongst the speakers of today you enjoyed the most, we'll send out a survey, you can fill it up, and you can tell us who should be the biggest WIMP. Maybe it's you. Maybe you could be the biggest WIMP, but we'll find out.
Pizza if you want.
Oh, yeah. So please give a warm round of applause to Kyle Thompson on Sheaves and the Serre-Swan theorem.
Is this?
Oh,
It's not up on the thing.
My bad. There you go.
There we go. There's me.
I got it.
There's the slides. Cool. All right. Do that. Good. Give it a minute for people to get settled in. I've got time. Fine. All right. Hello, I'm Kyle, and I'm here to give a talk on Sheaves, mainly Sheaves, and then at the end, depending on how much time I've got left, some discussion of the Serre-Swan theorem, which is really cool correspondence. I can state reasonably basically. So if you take one thing away from this talk, it should be that the way to study geometry is by studying the functions on a space. Right. This is how you should be studying geometry generally. If you've got geometry is the study of, I guess, a space with some structure. What kind of structure you put on it depends on who you ask. I think me and a lot of other people would agree that the correct structure to put on a space is a sheaf, or it's just something that looks like a set of functions. So if we just think with it, there's titles, I guess. You can see which one I wrote most recently. So let's do some motivation, right? So what's the easiest shape to deal with? That's the one we know most about. It's the circle, right? So we want to be able to study the circle by looking at the functions of the circle. So let's choose some functions, right? We've got x squared, y squared, and this weird thing over here, which is just x plus y squared minus 1 plus x squared, if you notice. And we can see already, like if we let's imagine we can like compute whatever we want. We can compute like any function at any point. We just can't like look at the shape itself, I guess. We can see already, like if we compute x squared, we can see that at the top, at the left and the right points, it's going to be, x squared equals 1 is only going to have those two solutions on the side. Is this working? There you go. That's those two solutions here. X squared equals 1. But if you had x squared equals a half, you're going to get like 4 solutions up here. Right? So you can see already that like by studying what these functions look like and what values they take, we can get some like kind of idea of the shape of the circle. So looking at the x squared one, we get that it has to look like this maybe. And then we look at the y squared, it looks like this. So we know it's going to have to look something like this, just by computing what these functions evaluate to at all the points. And in fact, we can go a bit further, right? So let's say we compute some values. So let's say we can get given a point and given a function, we can compute it, right? We compute some points on the circle, and we notice some patterns, right? We notice that f always evaluates the same as h, right? These are always the same function. Remember what the functions were? They were those there. And also we can see that, or maybe a bit harder to see, we can see that if we add f and g together, we always get 1. Right? So if you notice this pattern, right? We take the functions and we see that, wrong way? Okay. We take our functions and we see that all functions are going to be the same as long as they differ by a multiple of x squared plus y squared minus 1. Right? This is just a thing we can find by computing functions of the points, right? So we can see that all of our functions is going to be given by this ring here. It's the functions in x and y such that x plus y squared minus 1 is 0, right? And so just by looking at the functions, not any of the other data of the system, we can see that we found the equation of the circle, right? All we have to do is compute like a bunch of, I mean, we had to compute a lot of functions, compute every function on the circle at every point, so it's a lot of work, but just what I'm getting at here is the data of the circle is the exact same data as the data of all the functions, right? So we can see that there is sort of an isomorphism between looking at functions and looking at the geometric structure. For a more complicated example, for more information, we can learn by looking at functions. We take the cuspidal cubic. It's an annoying little shape. It's got a little cusp here in the middle, which makes life awful sometimes. It's shape parameterized by this thing up here. And we look at the functions here. Wrong way. Yeah, we want to be able to detect this annoying point with functions. And we can do that, right? So what we want to do is we want to get rid of this. If we want to get rid of this point, we want to undo our parameterization up here, which would require computing y over x, right? Because t cubed over t just gives us back to t. But that's not a well-defined function on this curve because it has a failure here. And in fact, this is the function that gives us the most trouble when it comes to this curve. So we have this theorem for algebraic curves that it's smooth only when the ring of functions is so-called algebraically closed. I don't expect anyone to know why this should be true immediately. But yeah, we see that, wait, what am I saying? Yeah, we can detect smoothness of curves at least by looking at this ring of functions is the point. It's just a well-known theorem. And we can see that in our case, we have a failure, right? We have y over x squared is the same as x. So therefore, it satisfies this polynomial here. I guess we say u squared minus x, right? Satisfies that polynomial. So we can see that this curve isn't smooth just by looking at the functions on the curve, looking at the ring of functions on the curve. And we can do better as well, right? We can find where this singularity point is. We can do so by, well, we know where it is, right? It's at 0. So if we consider the open set containing all the points except for 0, like that, we just remove the 0, then we can compute the functions defined on this curve. And now we've got no problems, right? Because y over x is now a well-defined function, right? We can divide by x because x is never 0. Our problem goes away, right? Our ring of functions is integrally closed. It's as nice as we can get, right? So by studying the functions on the space, we've found where the singularity is. Another way we could have done this, by the way, I think I mentioned it, is by slowly zooming in on points. We can see that the integral closure is it's always going to fail here. But other points, if we zoom in, it stops failing, right? So we can, by zooming on different points, we can also find problem points by just looking at the functions. Instead of being functions like on a set, we look at the functions near a point. These are two very common things that we're going to generalize to Sheaves. So what structure did we really use it? We used the functions on the space, and we used one of the functions on like an open subset of the space, right? Because that let us separate our problem into this point and other points, right? So we can generalize this. So the first thing we want to do is we want to package our open sets into a nice place. There. So we have what's called topological space. Guys, if you haven't seen categories, don't worry. It's just a way to hold the data of all of your open sets and all of the inclusion maps, right? The reason we would need the inclusion maps is because I mean, well, it's very fundamental to what a lattice of open sets would be. And an important part is that, let's say we actually have a set of functions, right? If we've got, a whiteboard pen actually. Let's say we've got a function defined on some open set, it's f. It's going, oh yeah, there was a thing, I forgot about that.
Do you want the board?
It's fine. Yeah, that's fine. We'll just leave it there for now.
Just leave it here.
I'll fiddle with it later, don't worry. So let's say we've got a function defined on some open set here. Let's say this is going to like, we'll just call it k, I don't know, some place. It's a function on this space, on this open set. And then we've got a smaller open set. Well, there's a natural way to turn a function on this open set to a function on this open set, right? We can just take f restricted to this like open set, right? So when we're looking at the structure of functions, we do really care about when there are inclusions between the sets. And so if we have an object that has these properties, let's figure out which preset I need. Is it this one? A preset, which one? Perfect, wonderful, 3. Cool. So if you've got a structure that supports these restriction maps, it looks something like functions, right? It may not look perfectly like functions, but it looks somewhat like functions. We say this is called a pre-sheaf. It's not a sheaf yet, but it's getting close, right? We've got some of the fundamental properties of functions. There is, however, another property. Yeah, we'll just leave it there one that we really want for functions, and this is the really important. So let's say we've got some functions. We've got open set here, we've got an open set here, open set here, open set here, and so on, right? We've got maybe a covering of open set. And then we've got a function here. So yeah, we've got function defined here, function defined here, function defined here, function defined here, right? Then, as long as these functions agree here, there is a well-defined function on this whole thing, right? Where at each point we just take whichever function we can choose, because no matter where we are, it's going to agree with the functions. And this is the most important part of being a sheaf. It's called the gluing property. And this is all it's saying. All it's saying is that when you've got functions that are all agree, they extend uniquely to some global function. So you can write this, again, I don't expect people to know what categories are, but you can write this really succinctly as this equalizer, which is basically saying everything in here that if they restrict to the same thing down here, then they come for a unique thing here. It's all it's saying. Right. So yeah, we can now define sheaves. So sheaves are just a pre-sheaf. A sheaf is just a pre-sheaf that, what am I saying? Yeah, a sheaf is just a pre-sheaf that satisfies this gluing axiom, right? So we've got an open set. If we've got things that agree on restrictions, then we can lift to the global set. So we've got a bunch of examples of these sorts of space, these sort of objects. So for I'm writing a reducible here because I forgot that was a requirement until this morning. For a topological space, we can have just the constant sheaf, where you get a constant, right? This doesn't really look too much like functions, but it's still a sheaf, right? It still works with gluing. It still has restrictions. We've also got what's this? Oh yeah, this is a very, very standard example. So if we've got two spaces, then we consider the sheaf of functions, right? This is the prototypical example, the sheaf of functions from a space to another space, right? In fact, right, so what I've defined thus far is what's called a sheaf of sets. So each open set has associated to it a set of functions. We could just as well define a sheaf of rings or a sheaf of abelian groups or something like this, where your sheaf takes takes values in some other category, so rings, abelian groups, and all this. And then the restriction maps have to be, of course, like ring maps or abelian group maps or anything like this, right? As long as as long as the definition makes sense, it's all fine. All right. So if Y is a ring, then we can have this even stronger thing, right? We can have all the maps onto the ring because now multiplication and addition is defined because it happens in the image. So this gives us an example, one of the main examples of a sheaf. So this is where it has applications to differential geometry. So for a manifold, we can define a sheaf by just taking all the smooth real valued functions. All right. In fact, I think I'll see later on that this is how I'd rather define manifolds because it's just better. Yeah, we've got the sheaf of real valued functions is a very, very important thing. Another one, just like the ones we had before, we had these like affine curves. You could do this for surfaces and stuff like this. So for any variety, really, we can get the sheaf of regular functions. These are functions that are well defined and they're purely algebraic. All right. Oh yeah, and then probably the most important example here is number 6. So this is the sheaf of sections of a space. So I think this one, where's the camera looking? I can see the whiteboard. this is possibly the most important one. So if we've got, let's say we've got some space here, and then we've got another space that like projects down onto it, then we have a sheaf of maps from this base space up into the big space. So we just take, let's say we take this point that goes here, this point goes here, this point goes here, and so on and so forth. And this is called a section, right? So it's a map that when you go up and you go back down, nothing changes, but you can go up. Right? This is kind of obviously a sheaf because it's a set of functions and it's well defined locally. And if you've got local things, you can obviously glue, right? It is all perfectly well defined. And this is probably the most important example of a sheaf because it will come up later. Right. Yeah, so I've defined the structure of a sheaf, but I haven't really attached this to any spaces yet, right? So, gosh, this is right. So if we just have a sheaf, so we let's say we've got a space, and then we choose a like distinguished ring space, a distinguished sheaf of rings on it. This gives us the structure of what's called a ring space. So it's just a space with a sheaf of rings. And now this is good, right? This gives us a lot of the structure we want. But it does fail in some ways. Well, it doesn't fail, but it doesn't have all the properties we want. So, okay. So I remember earlier when we were talking about looking for the singularities, we discussed zooming in on a point to find the functions near that point. This generalizes to this concept of a stalk. So I can draw another diagram for this. So let's say we're on the real numbers or something. We've got a function. We've got this function here. So it's just a straight line. And then we've got another function where it comes up, comes down, and then it completely flattens out and it goes up. Something like that, right? And then we can see that according to this point, as far as this point is concerned, these two functions are the same thing, right? It can't tell the difference. So we want some way to do that properly. So we can just do it. You just take all functions and neighborhoods, and then you say two things are the same if they are locally the same. And this defines what's called a stalk. This is incredibly useful for differential geometry, for example, because if you want to find the derivative of a function, you only really care about what happens near a point, right? You only care about the local behavior. And so when you're finding the derivative of a function, you only care about what this structure here, the germ, which is an element of this stalk. And we'll come back to this picture. Come back to the picture. This has a really nice property, right? So I've kind of drawn it. Yeah, we'll keep this drawing. We can see, right? So let's say this is y equals 0. Then this function here, it could like come down here and come down here. It could have some awful structure around here. But because it evaluates away from 0, right? Because it evaluates away from 0, there is some neighborhood where it's completely away from 0, right? So that means that we can define, so let's say this is f, this horrible uppy downy thing, it's f. Then near this point, so let's say this is x, we can define 1 over f, right? This is a well-defined because we're not anywhere near 0. So this means that, oh, and also if a function evaluates away from 0, then it has an inverse because it's locally non-zero. And obviously, if we go through 0, then it can't have an inverse, right? So this kind of gives us the last main property we need for, we want to look like functions, is we want to have this, what's called maximal ideal. So a maximal ideal is just a thing that when you're in it, you're, an ideal such that when you're in it, you're a non-unit, and when you're not in it, you are a unit. And we can see that in every reasonable case, we'll have this ideal of non-zero functions, right? Yeah, well, functions that don't evaluate in 0. And this is a maximal ideal. And so we define our the actual correct place to do geometry as called a locally ringed space, which is a space along with a sheaf of rings, so a ring space, such that at every point we have this lovely property here where if we're away from zero, we're invertible. If we're not at zero, we're not. Right. And these are like, in some sense, the correct place to do geometry. Right. So we've got some more examples now, right? So for any manifold, this is a locally ringed space. I mean, this is exactly the example we're doing over here, right? If we're away from zero, we're away from zero, so we're invertible. So in fact, we can take it as a definition that a manifold is a locally ringed space that's locally just the same as the real numbers with this sheaf here. So this sheaf here, remember, is the maps from Rn to R. I realize I've written this, I formatted this poorly, that n should be lower down here. Sorry about that. So this is the smooth maps from an open set to R. I think this is a better definition for a manifold. So the standard definition you'll see includes choosing atlases and stuff like this, which means like your manifold has to remember how it's cut up, and that feels wrong to me. This is nice. This is purely intrinsic. It's just there is a local isomorphisms to these sheaves here, and this lets you define. There's good books about this. Global Calculus, I believe, is one of them. Where you can define the differentiable structure of your manifold purely in terms of these sheaves, and you can do a lot more than you'd expect. Basically, coordinate free using sheaves, which is nice. Another example is our case for an affine variety again. So we just take our sheaf of functions again. This is just functions on. This is like polynomial or regular functions onto onto, I guess, our base fields. It's over some algebraically closed field. We also got this horrible thing here. This is the standard thing you'll study in algebraic geometry. It's the spectrum of a ring. It's a horrible definition. I don't expect anyone to care about it too much. But it's defined. It's essentially defined so that these stalks we've defined over, we remember from earlier. These stalks are the localizations of the ring. That's essentially why it's defined. And then we can generalize this. So this is the main, I guess, the more main thing you do in algebraic geometry is structures that locally look like these affine spaces. So with manifolds, we've got structures that locally look like Rn, and then for geometry, we've got these structures that locally look like rings. Okay. So now we've defined the objects of study. So we can now like do some stuff with them, right? Right. So once we've got a space with some structure, how do we study that space? By putting some more structure on it. So we define this thing here, which is maybe a bit weird looking, but it's not too bad, right? So we've got our space, which assigns to each point a ring. Maybe it could be if you imagine it's a field, let's say, then the natural structure to put on top of a field, it would be a vector space, right? It's the natural thing that lives over a field. Except now we're dealing with rings, so we just take instead of having a vector space, we'll deal with putting a module over our ring. So we say sheaf of OX modules here is just a sheaf of abelian groups such that each thing is a module over the sheaf of rings. It's just the only thing you really can do. I think I mentioned here at some point, it's reasonable to think, hey, what if we consider all of these? Does this look like a sheaf on an additional sheaf structure on top of this? Which I implore you to Google what stacks are, and it's quite fun. So one natural structure we could put over just a general space, really, is a vector bundle. Well, not a general space, but over spaces we come into a lot are vector bundles. So a vector bundle, kind of like this thing that I've drawn here, is we've got our original space here, and then at each point we've got a vector space, right? And these are glued together nicely enough, so it's locally trivial. So if we zoom in enough, then this just looks like a normal product of spaces. What am I going? Right. Since it's a space over our space, we can do the sheaf of sections. Remember from before when we've got all the maps going back up. And with vector bundles, we can see exactly what this structure is. So suppose we've got a vector bundle, right? Globally, we can't determine what the structure is going to be. However, locally we can, right? Because locally it just looks like a product. So if we, so zoom in to where it's trivial, and then the map literally just looks like projection. So we can say it's the trivial bundle. So we can identify it with just, so that we're saying, let's say we're in a manifold, right? This is a vector bundle over a manifold. And we zoom in, and locally this just looks like our space times Rn. Right? And so what does a section look like of this sheet? Well, a section is just, well, in the first coordinate, it's got to map to itself, right? It's got to map that down to itself. And then the next coordinate, it's got to be some real number, and then some real number, and then some real number, and so on and so forth. So we've got n copies of the real number, n real number valued functions, which means that, what does this mean? Right. And recall from the definition of the sheaf on a manifold that the structure sheaf of the manifold is precisely the functions on real numbers, right? So here we've got the data of a section here is the same as the data of n real valued functions. So the corresponding sheaf of sections is just n copies of the original sheaf, right? So if a sheaf has this property, we say that it's locally free and of rank n again. I think possibly sometimes you need some coherence conditions, but that's too much effort to put into this talk, which is meant to be very, very basic. All right. So in fact, this allows us to define vector bundles more generally, right? Because this correspondence is so nice, we can define vector bundles generally as a sheaf of OX modules that's locally free, right? Or we can say that it's rank n if we want it to have nice properties. Right. Awesome. Right, sure. So we want to study, if we want to associate to each open set a thing, and sometimes we're doing maths and we come up with a way to associate an open set to a thing that's not quite a sheaf, right? It doesn't have the gluing condition. And that makes life annoying because sheaves are lovely. They look like functions, and sometimes they have things that don't look like functions. We want to make them look like functions. So we can do what's called the sheafification of a pre-sheaf, I suppose we start with. So a lot of words. Okay. So what am I saying? The pre-sheaf. Yeah. Okay. So if you've got a space over another space, this is like our canonical example of a sheaf with sections on it. We can see that when we zoom in on a point, the data of the zoomed in version of the stalk is going to be the data of everything that lies above a point, right? I mean, all of these things above the point. And so we want that to be our space generally. So we define, wrong way, that way. Set theoretically at least, we define our sheaf here. Our big, so, okay. In order to go from a pre-sheaf to an actual sheaf, we want to construct a space over it, such that it reasonably corresponds. Because we know that spaces over spaces always give us sheaves, so that's a good thing to go for. So if we wanted to make that space, we'd need all of the fibers, so everything over a point, to be the stalks, right? So we define it. We just construct this object here as the disjoint union of all the stalks, and then we glue them together in some topological way. But set theoretically, this is all that's going on. Okay. And then in order to get the topology on this, gosh, I don't think. Okay. In order to get the topology on this space, we well, for every section of our sheaf, we can define a section of this actual space by just mapping a point to whatever S restricts down to. And so we just take the topological space that has the property that these are all continuous maps, right? So that means that this sheaf is, what am I saying? That means that this is now a sheaf. We've got a natural map from our original pre-sheaf to this sheaf, right? By sending S to S bar, which is now continuous. We made the topology such that it is continuous. And then this construction is lovely, right? Any sheaf, we have a natural map. Every map of sheaves, it will factor through this. This is, I recall from this morning the word adjoint functor. What this is saying is that the inclusion and the sheafification are adjoint. I think the inclusion map here is the unit or co-unit. I can't remember which direction it is. So yeah, it's basically as nice a category as we can get. It's a reflexive subcategory. Okay, so that was quite a bit of geometry. So we move on to some more algebra stuff. Okay, so another way to have structure over a space, over a thing, you remember, is modules. So if we've got the ring of functions over the ring of functions on the whole space, and we've got a module over that ring, we want to see if we can bring that module down to a module over every point. The first problem we run into is that M isn't a module over all of these open sets, which is maybe a bit annoying, but we can fix that quite easily. So do some basic algebra. We want to turn our abelian groups into modules over whatever we want. And one way to do that is by formally doing it. Doing that is just called the tensor. So in this case here, we take Zn, we tensor it with Q, and we get Qn. Right? We've turned Zn into a Q vector space. All right. This allows us, yeah. So this means we can turn our module into a free-sheaf by just tensoring at each point. But this is going to turn it into a module over this, which is going to give it a natural sheaf and pre-sheaf structure of OX modules. There is still a problem though, that this may not be a sheaf. But luckily, we've sorted that out already. You can just take the sheafification. And so we can do, for every module, we can have a sheaf associated to it. Okay. A natural thing to then do is ask whether modules and vector bundles have anything to do with each other. I mean, they're both sheaves, but there's anything more going on. One thing, by the way, here we've sheafified. It's maybe not clear that this isn't a module, a sheaf already. But there's trivial examples that I could probably show if I need to. Yeah, so we want to see which type of modules vector bundles correspond to. So this is a purely algebraic thing. We say we've got a projective module if every map lifts through projections, essentially. There's a bunch of different setups. So one here is quite useful is it's direct summand of a free module. This kind of corresponds to the local freeness, I suppose. Okay. Oh no, I guess the reason it corresponds to local freeness is because over local rings, projective and free are the same thing. Can now finally do the statement that this whole thing's about. And I'm realizing that I don't think I've got enough content to fill the time, so I might have to finish early, I guess. We can finally state the theorem, and that is that the correspondence it's always there, right? It's pretty much always there. Whenever you've got projective modules, so here's the thing, differential geometry. Whenever you've got projective modules, you've got vector bundles, and when you've got projective modules, got vector bundles, you've got projective modules, got vector bundles, right? And these are all special cases of a very powerful theorem, which I'm going to put up here. A lot of words. Do I understand all of them? Not off the top of my head. And I am 15 minutes early, and that is all the stuff I prepared. So I guess I'm done. Sorry. Yeah. Any questions or not? Just go.
When you are talking about the stock, is that related to the definition about the germ, the differential geometry?
Yeah, I mean, exactly it is. Yeah. So the stalk is made up of all of the gerbs of functions, right? So all the functions defined locally. Right.
Thanks.
Yeah.
Could you please elaborate a bit about the space of over a space within sheaf? So I kind of understand how the pre-sheaf works, but then space over space satisfying gluing, how does that?
Oh yeah, sure. So we'll rub out this one and redraw it. So we've got a space, and then over it we've got another space that projects down onto it. And then to satisfy sheaves, you need, what is it? It's restrictions and gluing, right? So if you've got an open set, and you've got a section over the open set, then this thing obviously restricts to a section over this open set, right? So the restrictions are all fine. And then if you've got, let's say, a section over this open set, a section over this open set, so this looks like this, and this looks like this. So remember, they have to agree on the intersections. Then, well, this is what I've just drawn is a section on their U, right? So we can always define the gluing of two sections. So this is like the prototypical example of a sheaf. So in order to do the sheafification, we get something that we turn our space into something that looks like this. We turn our sheaf into something that looks like this, and then we just say that that is now a sheaf because it always is. Is that? Yeah, sure.
What's the difference between open and globals, like these terms, like globals, like this?
Oh yeah, I guess I can go. Should I go through some of these words? I guess. So saying it's finally generated by global sections just means when you've got functions globally that when you restrict down now generate our sheaf. The admissible subcategory is the more of the meat of the theorem. So it says that a sheaf, what was it? It has to be, your subcategory has to contain all HOMs. So for any two sheaves, you've got a sheaf with maps between them, between the two sheaves. And it's got to contain all of those. And then it also has to be, everything has to be acyclic, which is a word, I suppose. So I guess I can explain that, I've got time. Acyclic just means that all of the higher sheaf cohomology groups vanish. So this is a lot of derived stuff. But essentially, if you've got a sheaf, you can take the global section, so all of the functions, and then this correspondence sending a sheaf to its set of all of the functions, its global sections, is, I'm gonna get this wrong way around, I'm sure. Right exact? I think it's one of the exacts, which means we can take its derived functors, which are essentially a way to do homology to a functor. And then if the higher ones of this vanish, then we say that the object is acyclic. And then we've got this admissible subcategory also has to contain all locally free sheaves. And then that's the setup for this theorem. And this just says that when those requirements are satisfied, then we do have this exact Serre-Swan correspondence. Is that helpful? All right, is that everyone? Cool. Yeah, I've given this talk before. I thought I had added enough content, but I suppose I hadn't. You guys are free to do whatever you want, I guess. Yeah. Didn't have enough content.
That's fine, that's fine.
I guess I should.
Could have
Because if you haven't seen Sheaves before, then it's a lot.
Yeah.
You live and you learn.
I will end the meeting and the recording on my laptop.
It's like fun thing. It's multiple version and Sheaves is just like some of those.